viewers. Today we are going to be going into thermodynamics relation as we have done in our previous lectures. Today we are going to be deriving the equation for internal energy and for enthalpy as well. So first we are going to be deriving an equation for internal energy. So internal energy we know is a function of temperature and volume. So we can say U equals to the function of temperature and volume. So now what we are going to do next is that from our previous video, if you have watched our previous video, we have made some emphasis on fundamentals of partial derivation. So now from this relation, we can say that the U is equals to the partial derivative of U over the partial derivative of T, keeping V constant, the T plus the U over the partial derivative of V, keeping T constant, V. So if you want to know how we arrive at this, you can go to our previous video and you will watch and see how we arrive at this. So next what we are going to do is this. We know that from our basic law of thermodynamics, we know that the U, that is the partial derivative of U, is equals to Cv, the partial derivative of T. Now this is for an isochloric process, which is a constant volume process. Now next, we are going to be making Cv the subject of this relation. So we are going to be dividing both sides by the partial derivative of T. So if we divide both sides by the partial derivative of T, we are going to be having Cv to be equal to the partial derivative of U over the partial derivative of T. So this is what we have. So next, we are going to be substituting the value of Cv in this equation. So next, what we are going to be doing is we are going to be substituting Cv, the value of the partial derivative of U over the partial derivative of T, keeping V constant, which is Cv in this equation. So we have Cv in this equation. So if we do that, we have the U to be equal to Cv dt plus, we have the U to be equal to Cv dt plus the partial derivative of U over the partial derivative of V, keeping T constant, dV. So this is what we have. So this can be referred to as an energy equation for internal energy. But for further modification, we can further simplify and say that by saying enthalpy, by using enthalpy. So now we know that enthalpy, which is entropy rather, is denoted by S, is a function of temperature and volume. So from the basic knowledge of our fundamentals of partial differentiation, we can say that the S is equal to the partial derivative of S all over the partial derivative of T, keeping V constant, the T, plus the partial derivative of S over the partial derivative of V, keeping T constant, dV. So this is what we have. Now from our first law of thermodynamics, we know that the Q is equals to the U plus P dV. And from our second law of thermodynamics, we know that T ds is equals to the Q. So if we equate both equations, we are going to have T ds to be equal to the U plus P. This is what we have. after equating both equation one, both equations. This is what we have. So next, equal to the s in this equation. But before we do that, we are going to be making the u the subject of this relation. So to make the u the subject of this relation, we have the u. So we are going to be making the u the subject of this relation. So we have the u to be equal to t ds minus p v. So this is what we have. So next, we are going to be substituting the value of the s, which is this, for the s in this equation. So if we do that, we are going to be having the u to be equal to c into the bracket of the s, which is this. This is what we have. We have just substituted the value of the s in this equation. So we put a minus p dv here. So this is what we have. So next, we can just go further and open this bracket. We multiply through this bracket by t. We are going to have the u to be equal to t into the bracket of the partial derivative of s all over the partial derivative of t, keeping b constant dt, plus t into the bracket of the partial derivative of s over the partial derivative of v, keeping t constant, dv minus p dv. So this is what we have. So next, we are going to be factoring out dv from here and here, because we have dv here and we have dv here. So if we do that, the u will be equal to t into the bracket of the partial derivative of s over the partial derivative of t, keeping v constant, with t, plus the bracket now of t into the partial derivative of s over the partial derivative of v, keeping t constant, dv. So sorry, we are factoring out dv. We have minus p, we have dv here. So this is what we have. So we have called this equation 1. We can make this to be our equation 2. So this is what we have. So next, what we are going to be doing is that we are going to be comparing both equation 1 and 2. So I will write equation 1 and 2 on the board. So next, equation 2 says the u is equals to t. Next is that I'm going to be comparing both equations. So if I compare both equations, I'm going to have Cv to be equal to, what we are going to be doing here is that we are going to be comparing these equations. So as you can see, we have dt here and we have dt here. It means we can say that this equation is equals to this, and we have dv here and we have dv here. So this is equals to this. So what we are going to be doing is cv now, which is having dt as the coefficient, is equals to t into the bracket of the s over the t of v, wherein is the coefficient of the t. Also, for this, we are going to be having the u, which is the partial derivative of u over the partial derivative of v, keeping t constant, will be equal to t into the partial derivative of s over the partial derivative of v, keeping t constant, minus p. So this is what we have. So now we are going to be comparing these equations with the Maxwell equations. Now we know that from our previous video we have proven Maxwell equations, and we know that Maxwell equation, from Maxwell equation, the s, keeping t constant, to be equal to all over dv, keeping t constant, that is from Maxwell equation, to be equal to the p all over the t, keeping v constant. We have proven this equation from our previous video on Maxwell equations. You can watch that for further understanding. So next, what we are going to be doing is that we are going to be comparing this with our Maxwell equation. Our Maxwell equation, that from here we have the partial derivative of u over the partial derivative of v, keeping t constant, be equals to t into the partial derivative of s by the partial derivative of v, keeping t constant, minus p. So this is what we have. So next, as we said earlier, we are going to be comparing this Maxwell equation, which we are proving from our previous video, with this. So if you look at this equation, we have the s, that is the partial derivative of s over the partial derivative of b, keeping t constant here, and we also have the s over the partial derivative of s over the partial derivative of v, partial derivative of s over the partial derivative of v, keeping t constant here. So next, what we are going to do is that we are going to substitute the value of this, which is this, for this in this equation. So if we do that, we are going to have the partial derivative of u over the partial derivative of v, keeping t constant, to be equal to t. So we are going to be substituting this value, which is the partial derivative of p all over the partial derivative of t, keeping v constant, minus p. So this is what we have. Now, if you recall from our first equation, that is our equation 1, we said that the u from equation 1, we said that the u is equal to Cv dt plus du dv dt constant dv. From our first equation, this is what we have. So next, we are going to be substituting this value, which is equal to this, for this in this equation. So what we have is the u. If we do that, the u will be equal to Cv dt plus c into the partial derivative of p by the partial derivative of t all over v minus p. So this equation can be defined. So this is what we have. So this equation can be said to be the equation used to calculate the internal energy of thermodynamic analysis. So we can say this is our equation. Let's rewrite it here. So this is what we have. So for the purpose of exams, if you are asked to derive an equation involving internal energy that can be used for thermodynamic analysis, we have this equation. It can be referred to as an equation involving internal energy for thermodynamic analysis. So this is what we have. Thank you for watching and stay tuned for more videos.